Hi dear students, this is the fourth part of the fourth module of the subject ME 206 Fluid Machinery. In the third part, we have derived an equation for the pressure head due to acceleration within the cylinder, and we have seen that equation as HA equal to L by G A by A omega square r cos theta, and we have seen that when theta equal to 0, HA equal to L by G A by A omega square r, and theta equal to 90 degree, HA will be 0, and when theta equal to 180 degree, HA value will be minus L by G A by A omega square r. That and all we have seen in the third part of this lecture class. Now at the suction side, pressure head due to acceleration is HA is equal to Ls by G A by AS omega square r cos theta, where Ls is the suction pipe length and AS is the suction pipe cross-sectional area. And at the delivery pipe side, pressure head due to acceleration HAD equal to LD by G A by AD omega square r cos theta, where LD is the length of the delivery pipe, AD is the cross-sectional area of the delivery pipe. This and all we have seen in the third part. Now we will move on to the next topic, that is effect of acceleration head on the indicator diagram. Now you have to see how this effect of acceleration is affecting on the indicator diagram. So this is the indicator diagram. This is the indicator diagram. That rectangular one was the ideal indicator diagram that we have already discussed in the first part itself. Now how the indicator diagram changes with respect to this acceleration head, that is what we want to discuss. As we have already derived the equation HA equal to Ls by G A by A omega square r cos theta, and we have seen that this HA value is depending on the value of the theta. Theta equal to 0 degree, HA will be having maximum value. When theta equal to 180 degree, the HA is negative, because cos 180 will be minus, that's why HA is negative at theta equal to 180 degree. See here, this point is the point where theta is 0 degree, and this is the point where theta equal to 180 degree. So at the suction stroke, the acceleration head is added to the already available head within the cylinder. We can see from the ideal indicator diagram, the initial head inside the cylinder is nothing but HS, suction head. This is the HS. This head is HS. So along with that head, the HAS value also will be added. HAS maximum value, because at theta equal to 0 degree, HAS will have the maximum value. So at the starting of the suction, the pressure head inside the cylinder will be HS plus HAS less than the atmospheric pressure. This line drawn through the center, that is this dotted line, is nothing but the atmospheric pressure head line. As I have already told in the first presentation, this value of the atmospheric pressure head is nothing but 10.3 meter of water. So below that we will have the HS value. So if you subtract HS plus HAS from 10.3 meter of water, you will get the pressure head inside the cylinder at the starting of the suction. That this point is the starting of the suction point. Now as the crank rotates through 0 degree to 90 degree, at 90 degree what happens is HAS value becomes 0, because cos 90 value is cos 90 is nothing but 0. Therefore HAS totally becomes Ls by G A by S omega square r cos theta. Cos 90 becomes 0, that means HAS becomes 0. So at the center of the suction stroke, that is theta equal to 90 degree, HAS value is 0. Therefore the actual pressure head acting inside the cylinder will be HS only. Now moving on to the last part, that is theta equal to 180 degree. As I have already explained, HAS value is minus HAS, because cos 180 is minus 1, that's why minus HAS. So initially during the ideal case, the pressure head inside the cylinder was HS. With that HS we are minusing that HAS value. So we will be drawing this one towards the upper side, that is from point B to upward we are drawing. Here we have drawn towards the lower side, here we are drawing towards the upper, that is to opposite direction we are drawing. Here HAS is positive, here HAS is negative, that's why we are subtracting. So total pressure head inside the cylinder will be H atmospheric minus HAS plus HAS, H atmospheric minus HS plus HAS. That will be the total pressure head inside the cylinder at the end of the suction stroke. Similarly, at the delivery stroke, at the starting of the delivery stroke, this point is the starting of the delivery stroke and this is the ending point of the delivery stroke. So at the starting of the delivery stroke, we will have an acceleration head HAD. We can calculate HAD from the equation HAD equal to LD by G A by AD omega square R cos theta. Here also HAD is depending on the value of the theta. So HAD at the starting, that is theta equal to 0 degree or 270 degree, whatever it may be, 180 degree, whatever it may be. Anyway, for the simplicity we are taking theta equal to 0 degree. For theta equal to 0 degree, HAD will be LD by G A by AD omega square R, because that cos theta term becomes 1. Therefore that HAD term is added along with the delivery head HD. So initially, if we consider the ideal indicator diagram, this point was the delivery head, corresponding to delivery is this point. Along with that head, we are adding a delivery head due to the effect of the pressure variation. HAD is added along with that point. So the total head at the inside the cylinder will be HD plus HATM plus HD plus HAD. At the middle of the stroke, theta equal to 90 degrees, so this term becomes 0. HAD will be 0 because cos 90 equal to 0, so HAD will be 0. At the end of the stroke, as I have explained in the earlier case, the HAD value will be just opposite to HAD in the starting point, that is negative sign will be there. So therefore it is subtracted from the HD value. So the pressure head inside the cylinder is this one, that means HATM plus HD minus HAD minus this much value, that will be the total pressure head inside the cylinder. So the ideal indicator diagram will have a slope, or it is reduced to a shape something like this. Actually it was a rectangle, now it is shape is moved to a trapezoidal shape. But you can see from this figure, even if the shape is changing, but you can see the area of this triangle will be equal to area of this triangle. So and also area of this triangle will be equal to area of this triangle also, because HAS, here it is HAS, here it is HAS, it is at the midpoint, here it is HAD, here it is HAD, and this is the midpoint. So area is not going, total area of the indicator diagram is not changing. So the expression for work done will remain in the case of this one also. So even though we are having an acceleration effect on the ideal indicator acceleration effect, the total area is going to be constant. We have seen in the second presentation that area under the indicator diagram will be nothing but the work done per second. So work done per second will be same whether it is acceleration effect is there or not, whatever may be the case, the work done per second is going to be same. That is one of the important thing you have to note down. And the next is at suction side HA equal to LS by G A by A omega square R cos theta, that is the general equation. Now hence the absolute pressure inside the cylinder during suction stroke is H atmospheric minus HS minus LS by G A by A omega square R cos theta. At the starting of the stroke, cos theta will be equal to 1, that is theta equal to 0 degree. So HA max equal to LS by G A by A omega square R cos theta 1. So at the beginning of the stroke, absolute pressure will be HA at atmospheric minus HS minus HA max. I have already, I think it is clear for you, I have already explained it here. I have already explained the same thing here. Let me correct it. Okay, one minute. So at the starting of the suction, that is the pressure, total pressure is at this point. This is the atmospheric pressure HATM. So HATM minus HS is this one, minus HAS. This is HAS. So HATM minus HS minus HAS is the absolute pressure head inside the cylinder at the starting of the suction stroke. Similarly, the absolute pressure at the end of the suction stroke will be this one, this point, corresponding to this point. This is nothing but, you can see this is HATM, this much is atmospheric pressure head HATM, and this is here to here it is HS, this is HS. So HATM minus HS plus HAS, that will be the total pressure head inside the cylinder at the end of the delivery stroke. That is what is explained here. At the beginning of the suction stroke, absolute pressure is H atmospheric minus HS minus HAS. Actually, it is HAS max. Similarly, at the end of the stroke, absolute pressure is HATM minus HS plus HAS max. At the middle of the stroke, as we have seen, HA max is not there. HA value will be equal to 0. So, at the middle of the stroke, the total pressure head is this one. The total pressure head is HATM minus HS. That will be the absolute pressure head inside the cylinder. Similarly, in the case of the delivery side, you can see here also absolute pressure head. Absolute pressure head at the starting of the delivery stroke is this much pressure head. This is H atmospheric plus, here to here it is HD, at H atmospheric plus HD plus HAD. So that will be the absolute pressure head at the starting of the delivery stroke. At the middle of the delivery stroke, total pressure head will be HATM plus HD, because HAD will be 0 here. This is HATM plus HD. HAD will be 0. At the end of the delivery stroke, what happens is H atmospheric plus HD minus HAD. That will be the absolute pressure head inside the cylinder at the end of the delivery stroke. Please go through the slide very carefully. Look 2 or 3 times, then you will get a clear idea. That is what is explained here at suction side and at delivery side. What will be the absolute pressure head at the end of stroke? So the minimum pressure head in the cylinder occurs at the beginning of the suction stroke. From this figure you can see the minimum pressure head is at this point. So during the suction stroke, the minimum pressure head is at this point, and during the delivery stroke, the minimum pressure head is at this point. So the minimum pressure head in the cylinder occurs at the beginning of the suction stroke. As the speed of the pump is increased, HMax also increases, because it is depending on the term omega. So if the speed is increased, HMax also increases. For a certain critical value of speed, the absolute pressure head at the beginning of the suction stroke reaches the suppression pressure head. So as we know, there will be a suppression pressure head. Suppression pressure head means the corresponding pressure. If the rotary machine is working at a particular high speed, if the speed goes on increasing at a particular speed, if the pressure is decreased too much, then there is a possibility of formation of the bubbles. That is what is known as suppression. Flow suppression will take place. There won't be any continuity of the flow. That is the suppression pressure head. So for each flow, there is a corresponding value of the suppression pressure head. For water and all, the suppression pressure head usually taking is 2.3 meter of absolute value. That is the suppression pressure head. So this minimum value max equal to suppression pressure. That is the condition for the suppression. That is at the suction stroke, the minimum pressure head is at the beginning of the suction stroke. That is HATM minus HS minus HAS max. That was the minimum pressure head inside the cylinder. This one was the minimum pressure head inside the cylinder during the suction stroke. That is at the starting of the suction. That is equal to H suppression. From this equation, we can find out the maximum value of the HAS maximum value we can find out. Similarly, if you discuss at the delivery side, what happens is HAD equal to LD by G A by AD omega square or cos theta was the equation. At absolute pressure in the cylinder during the delivery stroke is HAD H atmospheric plus HD plus LD by G A by A omega square or cos theta. That is the general equation. As we have seen, at the starting cos theta will be equal to 1. At the end also cos theta will be 1. So maximum value will be HMax. Maximum value of the HD max is LD by G A by AD omega square R. Now at the beginning of the stroke, absolute pressure is H atmospheric plus HD plus HAD max. At the middle, it is H atmospheric plus HD, and at the end of the stroke, the absolute pressure is H atmospheric plus HD minus HAD max. So from this equation itself, it is clear that the minimum pressure head is at the end of the delivery stroke. Minimum pressure during the delivery stroke is at the end of the delivery stroke. So if the suppression is taking place at the end of the delivery stroke, the equation is HATM plus HD minus HAmax will be equal to H suppression. So that is the general condition if suppression is taking place. From this equation, we can find out the maximum speed at which the pump can run.